Hi everybody, welcome to another video in discrete math section 4.4, solving congruence. So in this section we will solve this equation: a times x congruent would be mod m. Right, and the solution is that we define the a bar as the inverse of a, so it is congruent to 1 mod m. Right, now for example we say 5 is an inverse of 3 modulo 7 because 5 times 3 is 15, 15 congruent to 1 mod 7. Right. One method is using the inverse because we cannot multiply both sides, cannot divide both sides, but we can multiply by the inverse. And there's a plain fact here says that the inverse exists whenever a and m are relatively prime. Two integers a and b are relatively prime when the greatest common divisor is 1. We already know that. But if m and a are relatively prime, then that exists. And the way we do that is we using the Bessel coefficient to determine the inverse. Furthermore, a and m are relatively prime integers with m greater than 1, then the inverse of a modulo m exists. Right, let's just find out. So 3 and 7. So we use the division algorithm. We have 7 is equal to 2 times 3 plus 1, right? Now if we write this as 1 equal to 7 minus 2 times 3, or of course minus 2 times 3 plus 7, either way. But now we try to find the inverse of 3. So we just look for the coefficient, and the Bessel coefficient give us the inverse. So inverse of 3 is negative 2. Of course we can write it is mod 7, modulo 7, so we're just going to add 7 to this, 5, 12, and so on. So the inverse of course can be any this number, but usually we go with the positive numbers here. Right, so we write that as start from 1, and then we're expanding until we find the coefficient of the number we're trying to find the inverse of. If they, then that will give us inverse. Right, let's try to more complicated example. Find the inverse of 101 modulo 4620. Alright, now that's more complicated. Right, first I think there was a typo. 42620. Right, we just divide, and we use the division algorithm. 42620 divided by 101. It's not going to be nice and even, but it's going to be 421. It is 4620. So we start for 620 is equal to, we have 45 is the quotient divisors 101. We just need to get the remainder. So 4621 minus 45 times 11, 101, sorry, 75. Alright, next we'll go with 101 and 75. Sorry. Yeah, just go with the divisor and remainder. Like this is Euclidean algorithm. 75 is the divisor, but because there are only one times, and it will be 26. Now we'll look for 75 and 26. That's 2 times. $23. Now 22 and 26. Now 23 and 3. Now 3 and 2. And then 2 and 1. That's done. Right. Now what we do is we're going to write this in reverse and try to find the coefficient, the Bessel coefficient of it. Right. Now just write in reverse. And we start with, so that we will have 1. Right, reverse. From this we can just say this is just 3 minus 1 times 2. Now the 2 here is the remainder. Next, replace that by this. Right, now, look at this, we have negative 23. And 3 minus plus, so that is 7 times 3, which is 8 times 3. So look at that, we will take care of the remainder. We took care of 1, now we took care of 2. Next we took care of the next one, 3. So 3 is equal to 26 minus 23. So, and then replace that, so we still have 8. 3 will be 26 minus 1 times 23. So that gives us 8 times 26. Minus 23 minus 8 times 23. So minus 1, so minus 9 times 23. Next we will take care of the 23. Just 8 times 26. I just leave it like that. Why not? Now 9 and 23. 23 will be therefore still have minus 9, and then 23 is 75 minus 2 times 26. Right, now a in 26, that 18, a in 18, 26 times 26, and then we have 9 times 70, minus 9 times 75. Took care of that. Now took care of 26. Replace one, either one of them. With custom, replace that to the second. So be 101 minus 75. Or 1 times 75, that's the same thing. So that's the first one. Minus 9 times 75. So that's 26 times 101. And then minus 26 minus 9. 26 and 9 minus 35. Finally, we take care of the 75. Substitute in here. 26 times 101. And 75 is 4620 minus 45 times 101. Right. When we do that, we have negative 35 times 4260 for 620, and now we have 45 times 35 plus 26, 1601 times 101. Now the basic coefficient of 101 is 1601. So that is the inverse. So we have to do this and we substitute for all of the remainder in the Euclidean algorithm. So that's what we get. Right. Let's say now that we have the congruence, we have the inverse. How do we solve the congruence? Right. Very simple, right? So we start with 3x mod 7. That's the problem. From previous page, we know the inverse was what? Oh, inverse is 5. So we're going to use that. I multiply 5 on both sides because it is the inverse. That 15. By the way, of course, that is going to be 1. So that's the whole point of multiplying the inverse, right? This is 1. So that just gives us x. Then we multiply 4 on both sides, right? 20 mod 7. Right, 20 divided by 7 is easy. The remainder is 6, right? 2. Yeah. So this is just x is congruent to 6 mod 7. So that case x could be a lot of things. Alright, 6. Then we just plus 7, 13. Plus 7, 20, and so on. Of course, you can also subtract if we want to the negative. 6 minus 7, so minus 1, and minus 7 minus 8, and so on. So it can be either solution will be infinitely many solution. Right. Next, we have the Chinese remainder theorem. So in the first century, the Chinese mathematician, actually he's not only the mathematician, is one of the best general at the time, if not the best. Right. So there are things whose number is unknown. So we try to find something, right? When divided by 3, the remainder is 2. When divided by 5, remainder is 3. And when divided by 7, remainder is 2. What will be the numbers? So the reason of this way is this the method. So I did mention that he is a great general. So one of his way is he quickly can calculate how many soldiers present at the moment. So he asked them to line them up in 2 rows, and then tell him what is the remainder. Of course, if you divide by 2, you can only remainder is 1. I mean, actually divide, line them up in 3 rows, and then just the guy in the back will yell the remainder. So it could be 1 or 2. He write that down, and then he say, okay, now line them up in 5 lines, in 5 rows, and they do that, and they would yell the remainder, and they do that again for 7, and they do that again, maybe higher, but let's start with 7 here. So, and he only record the remainder for each time they line up in 3, 5, and 7, and from there he calculate how many people are present at the moment. So that actually faster than if we line everything on a straight line, then just count one by one, right? Right. So this also can translate into the system of congruences in that. Now so for X. Now let M1, M2 to Mn be pairwise relatively prime positive integers greater than 1, and A1 to An are arbitrary integers. I will write the problem like this. Notice that the A1, A, those are integers, and it has the unique solution modulo M equal M1, M2, M. So the M are relatively prime, and X will be a solution are congruent to M in that case, congruent modulo M in this case, right? And the proof, this is the proof by construction. So first we take the M as the product of everything, and then we construct the MK. Right, and after that we will find the inverse. YK inverse of MK. And then finally we have X is equal to this. Right, now let's construct things. So first, so this equation we have M, A1, little m, and now we'll construct A1, M1, and Y1. Right, so first we have modulo 3, 5, and 7, so that is M1, M2, M3. and the A is what it is modulo, so 2, 3, and 2. Two, 3, and 2. If you multiply everything across here, that we find M is the product of M1, M2, M3, 3, 5, and 7. That's 105, right? Right, so we have A, and we have, actually we don't have yet. Now we calculate the big M. The big M is by the M divided by little m. Big M is M divided by little mk. So big M1 is the 105 minus M1 at 35. M2 105 divided by 5, 21, and M3 105 divided by 7, 1, 15. Pretty much just the other two numbers. So we have M7, M3 is those two times together, big M2 is those two times together, and big M1 is those two times together. Right, now next we find the inverse, y1, y2, yn of the mk. So what are the inverse? Right, so the inverse of the mk are the big M1 most they. So first we say inverse big M most little m. So we find the congruent of, not the congruent, inverse, and M1 mod little m1 is that 35 mod 3. Right. So for those we just have to vary some very small number, and by inspection we can say divide by 3, right? So if we have 1 times 35, 35 divided by 3, remainder is 2, right? So that doesn't work. We want the incongruence one. So 2 times 35 is 70, 70 divided by 3. Yeah, remainder is 1. So we say 2 times 35, which is 70, is congruent to 1. So that's why they're inverse, mod 3. So with that, y1 is 2. Right, so we do the same thing. Now inverse of m2 mod little m2, big M2 is 21 mod 3. Right, now let's divide. By 5. Right, now 21 divided by 5, remainder is 1, so that's good. We can say 1 times 21 is congruent to 1 mod 5. So with this we say y2 is just 1. Now we have m3 mod big M to is 15 mod 7. Right, luckily 1 times 15 is 15, and that congruent with 1 mod 7. Right, 15 divided by 7 is 2 remainders 1. So if remainders 1 is good, so that means we found the inverse. So we have y1, y2, y3, and then finally x equal to that a1, m1, y1, a2, m2, y2, a3, m3, y3. So a1 2 big M1 35, y1 2, right? And then a2 3, m2 21, y2 1, plus a3 2 big M 15 and a3 is 1. So do all that. I have 233. So x equal 233. Of course, we can say that x is congruent and 23 is congruent to 23 mod 105. Right, but we solve for x and show that to 23. Of course, there are more. Could be more than this, but 23 is the smallest one possible. Right, so that is the Chinese-Roman theorem. Now next we have Fermat-Little theorem. Fermat-Little theorem. That not to be confused with the Fermat theorem about the famous 100-year-old problem and the solution just found about 30 years ago. But this is similar form. The focus now we say if A is an integer not divisible by P. P is prime, A is integers not divisible by P. Then we have A to the P minus 1 is congruent to 1 mod P. Furthermore, for every integer A, we have A to the P is congruent to A mod P. Right. So what we get from here is this. If we write, if in this case it's modulo 11, so that means P is equal to 11. So in that case we said we know A to the 10 is congruent to 1 because 10 is 11 minus 1. Mod 11. Right, so that's good. Now 222, how do we reshuffle that? So here we can do 220. We can write this as 7 to 222 is 7 times 220 plus 2, right? Plus 2, not really important. But what important here is we say 220 is 11 times 20, right? That gives us 220. And then the 2 by itself. Right. And 20 is, I will write 10 times 2, that's 20 times 11. Now we will write this as 222. But we do have this, right? And we said for every integer a, we have a to the p is equal to a. So that whatever this number is, so to replace that with 1, and so that is 49. And 49 divided by 11 is congruent to 5. Most 11, sorry. Yeah. So that's what we have, right? So the fact that this is the prime is 11, so we're going to write mod 11 and a to the 10. 1 less than that is going to be congruent to 1. So we start with that and try to rewrite power of 10. In that case, I'm sorry, the power base 7 to the 10. So that gives us 1, and the rest is simple, right? This is 11. A pseudo prime. I already mentioned this earlier. A pseudo prime is that in this form, even though it's not a prime, but we still call that pseudo prime, and it's very rare. We have to choose like 340 and so on. And the set form, this is a typo. Right, it's at 10 to the 10, which is 10 billions. There will be that much number of primes, but there only this pseudo prime. So pseudo prime is very rare. Right. Next we have primitive roots and discrete logarithms. So we say that primitive root module a prime p is found to be z sub p, such that every non-zero element of zp is a power of r. So anything in this called the group later on, everything in this set can be generated by number p itself. Right, so that's interesting. Now, since every element is a power of 2, 2 is the primitive root of 11. Alright, we need to show this fact first. Right. So 2 to the first power is 2, so that's good. 2 squared, 4, 3, 8. 2 to the 4, that is 16, and 16 when we congruent to 5 when we do mod 11. Right, 1, 2, 3, 4, there's 11 of them. Just keep going. 2 to the 4th, I already have that. 2 to the 5th, 32, and congruent, that will be 10. to the 6, 64, and when we mod 11, 66 is good, 64 is 2 less, so that will be 9. Then 2 to 7, 128, so that's more like 121, 7. And you see all the numbers are different: 2, 4, 5, 10, 9, 7. Right, 2 to the 8, 256. Like 23 times 11, and subtract them to, oh, that's a 3. Right, 2 to the 9, 512. First I have to divide by 11, so 46 times 11, and we subtract the 2, so that's 6. So say 6 mod 11, because that would be that number is less than 11, so we start. Right, 2 to the 10, we don't have to do that, it's going to be 1, right? The Fermat-Little theorem. 1024. Right. 1024 divided by 11. So 93 times 11, and we subtract from 1, so that is going to be 1. See, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Of course, we can generate all 10 from. Of course, the last one is the 0 power. Of course, you can always say 2 to the 11. But we're not doing that. I mean, the other number will be 0 in this case. There is a parameter proof of modulo p for every prime number p, so that is a theorem. So there's always this. And then next we define the discrete logarithm. If r to the e mod p is equal to a, right, for example, log base 2 of 3 this is terrible. Log base 3 equal to 3. I see discrete logarithm 3 modulo 11. So we say that E is the discrete logarithm of modulo P base R. So the base is the remainder. And we write log base R of A is equal to E. So here we say the modulo of 11. Discrete logarithm of 3 to the base 2 is 8, as 28 is equal to it's terrible. I should say it's not 28, it's not 28. It's always typo. Right. So we should say that congruent to 3. What's that? Okay, I think 3 and 8 was correct. But I said we're just gonna leave it like that, and this is where I want to stop section 4.4. As always, thank you for watching, and see you in another video in the Sweet Math.